Okay, welcome. So it is my real pleasure today to introduce the last event of the day for the people who are here for a visit day, mostly to introduce the seminar speaker, my colleague and friend Benedetto Piccoli from Rutgers. Benedetto is the Associate Provost for Research at Rutgers in the Department of Mathematics. He's obviously a well-known authority in the field of hyperbolic PDEs and a lot of the mathematical models that have been used for modeling traffic, supply chain, and many other things. He has published over 150 articles and 6 books. Received his PhD from the University of Trieste and had many positions over the year. The most interesting one being at CNR in Italy, and I'll say a little personal story here. This is, I think, the only place in the world where I have seen mathematicians guarded with people who have guns. And so if you actually go to the CNR building, there's actually a guy with a gun, and you have to talk to that guy before you can go to Benedetto's office. And the really scary part is you really think that this guy with a gun could be really dangerous because it's not clear if he can even operate the gun. Without further ado, I think today we're going to hear about a really cool topic, which is the topic of Lagrangian control of vehicle, the next generation control, where control is not just static assets, but moving assets. And with this, please help me join welcoming Benedetto for this talk.
Thank you very much. Thanks. So thank you so much for this nice introduction, and I promise I will not talk about guns. It will all be about traffic. And there could be a couple of subtitles to this talk. One could be the story of my collaboration with Alex. So most of what I'm talking about will be indeed collaborative projects that we had with Alex. And finally, but from the perspective of mathematician. So what I will do is that I will show what some of the work that we have done over the years, and I will try to showcase the fact that there is a lot of non-trivial math involved into these type of applications. So let me start with the story going back to 2008. 2008 was the time in which there were the first work about using Lagrangian sensors to monitor traffic. By Lagrangian sensor, I mean something like the following picture, coming soon, I hope. Okay, so everyone knows here at ITS what was a benchmark, really a milestone in the history of traffic monitoring that was the so-called mobile century. So this was the experiment that the group of Alex and many other people, in particular ITS and other institutions were involved, ran. In this experiment, 100 cars had the drivers equipped with a mobile phone and an app on the mobile phone that was transmitting position and speed of cars. And this signal was elaborated and sent back to cars, showing the velocity profile. At that time, was more than 10 years ago, this was pretty revolutionary. Nowadays, we are experiencing this on everyone on our phone, right? And we have a lot of apps now that tells you about the traffic status, suggests you which route to take, and so on and so forth. But at that time, more than 10 years ago, was really an impressive achievement. So let me talk a little bit about what was, for me, the math behind that. So first of all, when we are talking about modeling traffic, like many physical systems, we need to decide which scale we are going to model in traffic. Yeah, okay, now it's working. So the first scale at which one may think is the microscopic one. And this started really probably around 100 years ago. People started using this model. So you have a number of cars on the road, and you identify the state of the system by assigning positions, AXI, and velocity VI of the ith car. And then there are various microscopic models. One of the most celebrated is the so-called follow the leader. You see, you are saying that the acceleration of the ith car is given by the ratio between the difference in speed of the car in front and the distance. So this system naturally tries to align the speed. Each driver tries to align the speed with the car ahead, and the alignment is as quicker as you are closer to the car in front. Because obviously, if you are very close, and the car in front is lower, you want to adjust your speed pretty quickly. On the opposite extreme of the scale is when you are looking the road from very far, and you assume that you are looking, rather than positions of the single cars, you are looking at the density. And this density of cars obviously is evolving in time. So the density will be a quantity that will depend in time and also the location on your road. Once you do that, there is a very natural equation that you can write that is given just by the conservation of cars. So it's based on the principle that the number of cars cars are not destroyed or created, and hopefully this is what happens most of the time on our roads. And then you write mathematically the conservation of car in the following way. The number of cars between A and B, say on this stretch of road, is just the integral of your density. So the change in time, the way in which this quantity change, must only depend on the flows. No car is generated or destroyed. So this will be just the increase because of the inflow from the point A, and will decrease because of the outflow from the point B. Once we decide that this is a basic principle that we agree upon, then we immediately can deduce an equation. We apply fundamental theorem of calculus, and then we do just a little bit of algebra, and we end up with this type of relationship. This is obviously a partial differential equation, and we are saying that the sum of the derivative in time of your density and the derivative in space of your flow is equal to 0. So this is called the conservation law, and as many of you know, a single conservation law is probably the first model that was used, the macroscopic model that was used in traffic, and more precisely, it goes back to the work of Lytle, Whitham, and Richards that proposed the very first macroscopic model. So their further step, beside the writing conservation of cars, is the following. Well, the flow is always given by the density time the average speed at that position in space and time. And their main assumption was that the speed is indeed just function of the density. As long as you make this assumption that is reasonably true in traffic, then you end up with a single equation. Because here you see you would have two variables, the density and the speed, but if you assume that the speed depends just on the density, you have a single equation. And this is the celebrated Lytle, Whitham, Richards. Obviously, the density is naturally bounded between 0 and the rho max, that would be the maximal density that reflects the capacity of your road. This is a typical, one of the typical velocity profile that you would use, a decreasing function of density, maybe linearly decreasing, as it was proposed by Greenshield in one of the first papers. And this gives rise to a concave flux. Already this equation that now is so widely used in traffic, it's highly non-trivial because it's a nonlinear conservation law. And since it's a nonlinear conservation law, it has a lot of non-trivial phenomena, like the development of discontinuities in finite time. And these discontinuities are called shocks. And these shocks travel in time. For instance, in traffic, we will see that they naturally represent backward moving waves, and they may represent indeed, for instance, queues at traffic lights or at when you have on-ramps and other phenomena of your network. So again, you see the fact that the solution would naturally develop discontinuity in time asks immediately for non-trivial mathematics, right? Because here we are taking the derivative of a function, and this function in general will have a jump. Okay, so when you take the derivative of a function that have a jump, what is its derivative is a Dirac delta, right? And this Dirac delta, sometimes people think as a generalized function, but the best way to think of it is as a measure. And we will come back, I will come back on what is exactly a measure, but the best way to think mathematically is something that acts on function, okay? Something more general that if you want to identify well is something acting on function. So this type of problems arise very naturally, and then immediately you have a problem also of uniqueness of solutions. And since you need to ask for weak solution, these are non-unique, and you need to introduce some criteria. And the most used and known one is the entropy condition that comes really from gas dynamics. It's known in gas dynamics that entropy well, increases or decreases over time, depending how you decide to define your entropy. But let's say usually the physical one increase in time. And this asking that the entropy will increase in time along solutions will identify indeed a unique solution. And that's the physically relevant one. And it's also very important in traffic as well. Okay, this is just, let me show you why it is important and is relevant. This was another experiment of monitoring traffic that we were doing in parallel. Meanwhile, here there was the Mobile Millennium event. So these are devices called clear boxes. They were mounted on cars by a company, Octotelematics, on agreement with insurance companies. That is something that is happening now in the last 5 years in US as well, very frequently. Your insurance company will give you a discount if you mount one of these devices that will monitor your speed, acceleration, and position. So you see, these are data that were collected back then in a large highway surrounding Rome. The highway is called GRA, and we were monitoring this, well, around 1/4 of this road. And these are the data. So this is a space along this stretch of road. This is time. And we represent dots if there was a car in that position at that time that was transmitting via these clear boxes the datum. And you see the dot is lighter, is larger and lighter color if the speed is higher, and is the smaller and darker color if the speed is lower. So essentially you should interpret here there is congestion. Okay? There is a more darker color and so on. But you see that probably I went, yeah, no, sorry. In this slide, I already depicted those two lines that are really bounding what was the evolution of this queue. You see here, people are, this is space, this is time, so initially there was no queue, then a queue starts to form and then propagate backward. And on the contrary, when we wait enough, the inflow is decreasing, you will have that this queue would resolve and this speed will be much higher later on. So if you use your conservation law, you can very well compute in these speeds. If you try to just understand that from data, it's not so easy. But if you use your conservation law, these are very natural speeds that are nothing but the so-called Rankine-Hugoniot condition that, by the way, I learned from Craig's book for the first time, obviously, like many generations of mathematicians. And so let me notice another phenomenon here that I think is interesting, because we are having in these days a debate about the tigers with Alex, about yellow tigers and white tigers, right? So the yellow tigers are these guys, the moving backward shocks. So the one that you observe everywhere, there is a traffic light, there is an accident, there is an on-ramp, whatever, and you see these shocks moving backward that we interpret as shocks in the sense of conservation laws. But then if you look a little bit more inside here, there are other tigers, the white tigers, and you see here that there is an area where the speed is higher. And here there is another area where the speed is higher. These are called the stop-and-go waves. So what happens is that you see you would have a very low speed, then you would accelerate, and then again low, then accelerate, and then again, and so on. So these are called more stop-and-go waves. These are different type of phenomena, and they do occur sometimes naturally without any factor triggering it. No junction, no light, nothing. If you have a large stretch of highways, they may arise naturally because there is difference in driving. And the other interesting point is that they appear a lot also when these more well-known waves called shocks appear. So typically what happens is that this is the well-understood shocks, but there are a lot of waves appearing there inside as well. And that's what, we call a white tiger because it's less explained where it comes from. But that's exactly what we will try to address, we are trying to address now. But let me, I would say, finish up the story and say that our collaboration started at that time because they had all this enormous amount of data from the Bay Area, and they needed a theory like the LWR, but to be applied to networks. And exactly at the same time in Rome, I was developing the theory of conservation laws of networks. So essentially, assuming you have a network, and on each link, On each stretch of road, you have your conservation law. But then you need to prescribe a dynamics at junction. What happens at junction? What type of rules you need to assign to make sure that you will have a unique evolution or a unique solution to your equation? Well, first of all, to understand what are the difficulties, I will use a very simple example. Assume you have a bifurcation, and your first road is completely full of cars, say maximal density, and the outgoing ones are free. Okay, so what's going to be the solution to this problem? Well, obviously, this is one solution, right? Everyone is turning right. But, obviously, we have many other solutions. One-third right, two-third left, and so on and so forth. So it's very clear that we cannot prescribe an evolution without assigning a traffic distribution matrix. Because if we don't have that information, if we don't know where people are turning, there is no way we will determine a unique solution. And this is expressed assigning a kind of origin-destination matrix, if you want, but bounded just at the junction. You assign coefficient that tells you J runs over outgoing roads, I over incoming. These are coefficients that are telling you how many cars from road I are going to road J. And that is a simple rule that was obviously used in many engineering journals and investigation since a long time. But what is a little bit a novelty is that this is not sufficient to isolate a unique solution if you put conservation laws on networks. And the reason is the following. Consider still the same problem, choose your favorite traffic distribution matrix, and voila, I'm giving you a perfect solution. Is this one? No one is moving. If no one is moving, this is a perfect solution. The inflow is 0, so your vector here is 0. Whatever matrix you choose A, your outflow is 0. No one is crossing the junction. Perfect solution. It satisfies rule F for any matrix A you may design. So indeed, you must give a rule saying that there is a will of drivers to cross the junction, and this corresponds, for instance, you may assume that the drivers are maximizing indeed the flux vector through the junction, and this is exactly an entropy type rule. Because if you think for a moment, if you assume those cars were more like a gas, the solution in which everyone stops is exactly the non-entropic solution, in which, for instance, in the very famous example of the two chambers, the gas stays just in one side and doesn't go to the other one. So this is really an entropy type. Now, this is a kind of claim that is not 100% accurate in the following sense. For simple junctions like this one, it is accurate. If you try to look for the solution maximizing the entropy, this is the solution. If you take a very complicated junction with many incoming and many outgoing ones, then the situation could be a little bit more tricky. So it could be that in that case you have more choices. These more choices could be, the entropy one could not necessarily be the one maximizing the flux. But for simple junction, it is. Okay, so this is the story of what happened in the past, I would say around 2008 or those times. And let's now make a jump in the future and go to 2016. So at this point, you see all that was about monitoring, so about understanding the system. And next step is obviously about controlling the system. So how can we control the system? Obviously, traffic engineers control the system since, again, since the birth of transportation, with the traffic lights, with signals, and other methods. Most of those controls are point-wise control, even if advisory panels, variable speed limiter may be not point-wise, may be more global. But there is another type of control that we can try to exert, that is through the autonomous vehicles or the connected vehicles. Those gives us a different paradigm for controlling the traffic system, because these are still, if you want, point-wise control, but they are going to move through your traffic network. So let me show you two movies. The first one refers to a very well-known experiment in traffic that was done in Japan around those years I was telling before, 2008 or so. They put a number of cars in a ring road that were equispaced and were traveling the same speed. But what happens is that there are differences between drivers in the driving style, reaction time, and so on. So soon they will start to have an area where they slow down and another area where they accelerate. And soon this will become a true wave. So people will essentially stop at a given point and then reaccelerate. And this given point is traveling backward in time. So this is exactly like the stop-and-go waves we were observing there in the data from Rome. Because you see, it's a complete oscillation of braking and accelerating, and this is moving backward in time like you would expect for a shock, for instance. So our first investigation was, okay, can we do something with the autonomous vehicle to address that? So this is the result of an NSF collaborative project between University of Illinois, Rutgers, Temple, and Arizona. And the idea was the following. Okay, these stop-and-go waves are problematic for a number of reasons. Well, first of all, you accelerate and brake, so for sure your consumption is going to be affected, and also the emissions, and also your safety somehow, because all these braking events is surely giving more chances of accidents. So in this experiment, we were trying to measure more clearly what was the effect of these waves, and also trying to dissipate them. So this is back in 2016 in Arizona. So we have the same setup of the Japanese experiment. The big arrow is over the vehicle that is capable of autonomy. If the arrow is black, the vehicle is human-driven. So you see here waves appears. Let me stop for a second because I want to explain you how to read all this information. So again, this is the vehicle capable of autonomy. Meanwhile, the arrow was black, the vehicle was human-driven. When it's red, it's implementing our control. In the first part of the experiment, you see there are some oscillations. Now, the dark line is the vehicle itself measuring speed as function of time. And all the other gray lines are the other vehicle. So you see that here oscillations start, and now they become a very clear wave as in the Japanese experiment. Now we start activating our control, and we try to dissipate waves. So meanwhile, you see the effect of our control. I want to point also the attention on the upper panel. So on the upper panel, we divide the experiment in different intervals, depending if there were starting of experiment, waves, and different target speed we were trying to achieve with our autonomy. And then we measure many different things. I will stop the movie soon to point more clearly the attention to the upper panel, but let me show you. You see here we were targeting many different speeds, and we were obtaining different results. Here we were pretty able to dissipate the waves. When we target at too high speed, the waves are showing up again. And now finally at the end of the experiment, we switched off autonomy, and so you see the car becomes black again. So let me point you to the upper panel. So again, this is the different intervals of the experiment. Initial, wave start, different level of autonomy, disable autonomy. This is the velocity standard deviation. Means that we collect all the data from all the cars. All the cars were equipped with OBD2. We measure a lot of data. And you see the standard deviation is over that interval of the experiment over all cars. So you see that the waves push up a lot the standard deviation. So there are more oscillations in speed. Something that you can see here heuristically, but it's clearly measured. And you see that we push down by far. So we reduced it to 1/3 of what was originally and 1/5 with respect to when the waves were present. But look at the fuel consumption. This is in liters per 100 kilometers. So why we use the liter per 100 kilometers? Because miles per gallon is a nonlinear function of the cost versus the miles you run. And there is even an article in Science of how much people perceive don't understand well miles per gallon because it's a nonlinear function, while liters per 100 kilometers is a linear function of, how much you would consume with respect to what distance you run. Anyway, whatever measure you take, here you see 18.8 was the average over all cars during that experiment phase. We had OBD2 again instruments, so we are not estimating fuel consumption with some model. It's really measured from the car data, and you see that the waves push up the consumption a lot. But look at our best result. We are decreasing with respect to wave up to 40% on the overall set of cars. So everyone is sparing 40% of fuel. And that was a result that went even beyond what we were hoping for, because we were promising around 15%. but this was really beyond our imagination. Obviously, this is a confined setting, so all numbers have to be taken with care. It's an experimental one. But look also at breaking events. They were 166, so breaking events were defined by a breaking of decreasing of more than 1 meter per second in your speed in a time span of 1 second. So it's an energetic breaking. So there were 1.66 events per vehicle per kilometers. The weights push up to 858, and our best result, we essentially eliminate a decrease of 98%. So just a 0.12. So this is another important result. So again, this setting is, is special. It's a ring road isolated in Arizona desert. But okay, even if you are not in Arizona desert, it's still a very special setting. So now what we are doing now in collaboration with Alex and Vanderbilt University and UPenn is to push this type of experiment effect to highway level. So obviously there is a huge number of headaches, safety, permissions, and so on. But fortunately, all that is Alex's problem. My problem is just to try to understand the math behind that and try to use more advanced math. So let me skip all those headaches and just focus on which type of math we are using. And the main aim here is to scare you to death by the math. So I hope I will achieve this goal. So first of all, we get inspired by something that is very well known in the fluid dynamic community, or even more specific, people doing kinetic approaches. So these are called the mean field limit and Vlasov-Tyke equations. So what happens is the following. This is my favorite way of writing things, so it becomes completely impossible to understand, right? No, so it's, if you think to your follow the leader model, you can rewrite in the following form that seems a bit complicated, but will be very natural then to pass to the mean field limit. So you see here I have still the car position, if you assume they are car. Their derivative position is speed. The derivative of speed you see here now, I write at the right-hand side that before was this ratio between difference in speed, difference in space, as a convolution operator with respect to a measure. So think that it's exactly the same thing I said before. But now I just write down in a slightly different way. So I replace a particle that was in position xi vi, so in position xi with speed vi, with the Dirac mass centered there. So assume there is it's just the same thing, but you are representing really by its mass instead by theoretical non-existing point. And then you sum up over all these Dirac masses, and you divide by the number of cars. This becomes a well-defined measure. Okay? It's a measure, so it's a bit more general than a function, but you see it's exactly defined as before. So xi vi are solving your OD, you are just writing this object in a slightly different way. And the dynamics you write in convolution terms just because it's nice for measures to write convolution. Okay? But it's exactly the same dynamic as before, no difference, you are just giving a different interpretation. Okay? These are measures. Okay, now what happens is once you do this step, under certain assumptions, you can pass to the limit. What does it mean you pass to the limit? You assume that the number of cars goes to infinity. Now, be careful here. We divide it by the number of cars so that we always keep mass 1. So it's always a probability measure. Now, in the limit, the probability measures satisfy a very nice equation called the Vlasov type of this following type. You see, here is your measure, that is your mass of cars. The derivative in space is advected by your speed. This is, nothing special. And then there is another term that obviously stems out of your second-order dynamics. So if you take the divergence with respect to speed, it's given by some acceleration terms that is just mimicking exactly what you were doing before. So the message is that in a very natural setting, you can translate, pass into the limit, and write a unique equation for all the cars, like you were doing with the conservation law. But you will have a few advantages. Now, just one comment. The problem of passing through the limit goes back really to the work of Kak, fundamental work suggesting propagation of chaos that is a very well-known and used techniques now by mathematicians working in the area. And I want to mention at least one work by Dubroshin that was the first one probably in passing to the limit in this setting using Wasserstein distance. What is a Wasserstein distance? I will tell you soon. So what we try to do is, okay, can you do the same with a control situation? So you see here I add the control because that's what we are interested. The problem is essentially no. So there are huge problems. One is that first of all is what is called indistinguishability of particles. So your control shouldn't distinguish between one car and another, and that obviously is a problem. And the other problem is that when you pass to the limit, you may end up formally with an equation of this type plus a term. This is your control. But in most cases, your control could tend to be singular. So now in measure theory, what happens is that you could have two very nice measures that they are, I mean, one inside the other, but they don't see each other. They are orthogonal. So what happens typically is that your limit could be a very smooth distribution, and very nice, indeed, it could be a function. And this control lives on a very strange set, for instance, called Cantor sets, so that their effect on the measure could be null. It could be zero effect. So one of my collaborators, Massimo Fornasier, likes to make this example. This would be like when you try to control a river with 1 billion toothpicks. You know, each toothpick is not really having an effect, and even if you put many of them, you will achieve nothing. So to overcome this problem, we took the following approach. So instead of passing to the limit in the whole population, you indeed assume that you will control a small number of cars. So you take a small subpopulation that has that you can control, and you have a large population that is uncontrolled. Again, here there is a lot of stars, but you know, essentially you are saying that the controlled one interact with the non-controlled one and vice versa. That's what you are saying. In this case, you can then pass to the limit, and you will pass to the limit essentially just in the uncontrolled one. And so you will couple one equation as before that is now coupled with these guys that you control. And this is perfectly fine up to the point that you can technically achieve what is called gamma convergence. So the interesting point here is the following. You can take your favorite, say, cost. This cost could measure, for instance, your fuel consumption, say. And this is typically a term that you put there to promote sparsity. So it's an L2, L1 term. Don't bother about that. And this is the limit functional. That is exactly the same function written for this equation. You have a gamma convergence. A gamma convergence, well, means that you have lower semi-continuity plus the existence of a sequence along which you have upper semi-continuous. But the important point is that you will have that the cost will converge to the cost, and the optimal controls will converge to the optimal controls. So you can use the result in both ways. In particular, if you are able to solve this problem, you can then try to apply to traffic, okay, to the real situation. So this was very nice, but you know, we thought that was not theoretical enough, so we moved a little bit to the next stage. So the next stage would be, okay, can we generate equations that are generalizing this idea of mean field limit? And so we came up with the idea of defining differential equation for measures that are really the natural generalization of ordinary differential equations. And the story goes as follows. Well, think to an ordinary differential equation as what is an ordinary differential equation? Well, you assign a vector field. Okay? What is a vector field? Well, there are many different definitions in math you can give. But essentially, let me think in this way. To every point over a manifold, think just Rn, a Euclidean space, you assign a vector. Okay? And this vector is something that belongs to the tangent space. Okay? You assume it's something that is tangent. So in mathematical language, when you put all your manifold with all the possible vectors on top, is you achieve what is called tangent bundle. It's nothing but your space plus all the possible tangent vectors. So a vector field is nothing but a map that assigns to every point on the base a vector on the corresponding fiber. So if there is a point, you assign a vector exactly at that point, not somewhere else. Okay? That's the only thing you need to do. Plus, obviously, some regularity, and then you obtain a nice ODE theory. Now, as I told you before, it's very natural in kinetic theory to identify points with Dirac masses centered at that point. So you can imagine that this is a map assigned to a Dirac mass on the base, a Dirac mass on the fiber bundle, and on the tangent bundle. And what you do is you just generalize that to any measure. So you assume you have any measure on your manifold, and now could be your distribution of traffic, and you assign a probability measure over your tangent bundle, whose meaning is essentially, if you look at the mass that is here, those are the speed along which the mass should be spread and should move. So it's, you see, this is a probability vector field. It's defined as a map going from the probability measure on Rn, for instance, let's stick to Rn, to the probability measure on the tangent bundle, such that if you project back, you should get back your measure. Because that's essentially the only requirement also here. You don't assign to a point here a vector down there. It should project down nicely. Once you do that, you can define a new theory that is pretty nice. Solutions have to be interpreted in a weak sense. Obviously, we already were doing this for conservation laws, so we have to do this also for this type of solutions. So they don't satisfy equation, but only when they are integrated against test function. And all this framework works very well. You can do existence, uniqueness, very natural generalization of ODEs, but everything must be based on the topology given by the Wasserstein distance. So let me tell you what is the Wasserstein distance. The Wasserstein distance or metric is also known as the earth mover metric by people working in image processing or operations research. So essentially, you consider the following problem. You have two measures or two masses, and these two masses are split, say, in small cubes. And you want to know the cost of moving one onto the other in the following sense. You are allowed to move one onto the other by moving each, say, single piece here over a single piece there. So obviously, you have many ways of making this move. This red goes to this blue, but could go to anywhere else. And the cost is the distance covered. So you see, if you take all these cubes and you send over these cubes, you have a lot of different ways of doing that. And each of one have a cost depending on how much distance you run will move all cubes. The optimal way of doing that is called the Wasserstein distance. Let me give you a little bit more of formula. So formally, you define the following way. So you have a measure mu and a measure nu. And the Wasserstein P distance is the infimum. Well, this was not exactly the Wasserstein distance, but this was the Monge problem initially considered. So you want to consider a mass that moves one measure over the other, and you integrate of all the run distance. You see, this is the distance between a point x, its image, and then you can put a p1 over p and so on. The problem is that here, this definition doesn't work that way, because indeed you may not have maps that send one measure over the other. And the very simple example is the following. If you have a measure that is a single delta, centered at one point, and another measure that is two deltas, there is no way that a map would split this mass in these in those two positions. And so you need to generalize that and replace your map by something that can split masses. And the natural way is to take a measure on the product space. So you see now you split this map in two pieces, and you essentially look for a measure in the product space that project nicely over one measure and the other ones. And this is a new way of transporting, if you want. You are allowed to split masses. So everything works well, and with this new definition allowing so-called transference plans, so you're allowed to split masses, you can have a well-defined distance called the Wasserstein distance. Let me briefly tell you that all the theory for measured differential equations can be developed strongly based on the topology given by the Wasserstein distance. So in particular, obtaining existence is easy with two very natural assumptions. If you remember how you obtain existence for ODE is in Peano theorem, you use two things. One is you need some kind of bound, okay? And this bound would be, your function could be locally bounded or sublinear growth, okay, if you want a global existence. And the second condition is continuity. This is Peano theorem. Then you have existence of solutions. And these are two conditions exactly similar to Peano theorem. This is a kind of sublinearity in terms of the support. And this is continuity, but obviously with respect to the Wasserstein matrix. Well, if you do that, you obtain easily existence. Now, continuous dependence, like the Cauchy-Lipschitz theorem, the one in which you ask your vector field to be Lipschitz, is more tricky. You cannot express that in terms of the Wasserstein distance. You need to define a more generalized object. The meaning is the following. You see here, this probability vector field V plays the role of our speed, right? So we need to compare a distance among two vector fields. The temptation would be, well, these are just now probability measure over the tangent bundle. Take the vast distance of the tangent bundle. It does not work. And the reason why it does not work is that, you see, base and fiber have a different meaning. The base is really the mass you are transporting, and the fiber is essentially a perturbation. So they cannot treat in the same way. The vastest distance over the bundle would mix up everything. So you need to do the following. You still take transference plans between the vector field, probability vector field, but you ask this transference plan to be optimal over the base. So you cannot mess up over the base. Over the base, it must be optimal. And then you measure its distance over the fiber. This works, but you have just to pay a price that this is not a distance. Because essentially you now are treating asymmetrically base and fiber, so it doesn't satisfy the triangular inequality. So you can still do all the Cauchy-Lipschitz theory, but you need to pay the price of having something that is not a measure. Let me just make the last remarks. This theory has been extended in various directions, and one result that I'm pretty happy of is the following. Now you can give a very natural interpretation linked to conservation laws. That was the equation we started at the beginning, and is the following. If you have a conservation law, you can isolate a solution prescribing entropy or prescribing what are called solution to Riemann problems, that are solution to simple problem with just one jump. And once you have one conservation law, you can define uniquely a measure differential equation so that the unique, you have an entropy solution here, if and only if its derivative is a measure, is a solution of the measure differential equation, and the uniqueness is given by what we call a Dirac germ. That means prescribing small time evolution of finite sum of Dirac masses that are exactly the corresponding on this side to what is called a Riemann solver. Okay, so there is a perfect one-to-one correspondence. Okay, so I hope that you were scared enough up to now, so I can stop and go back to say, okay, if you were scared enough, I want to recall you anyway what a long time ago John von Neumann was saying. That is, if people do not believe that mathematics is simple, it's only because they do not realize how complicated life is. And I want to convince you that indeed using measure and measure differential equation and mean field limit is indeed much simpler of what you indeed address every day. Because many of you do, most of you do research in transportation, and many of you specifically on vehicular traffic. Let's stop for a moment and think what you are trying to model. Okay? Well, you are trying to model a system that has at least 3 components. One is the big infrastructure, the roads, the signal, and so on. Then there are a lot of agents on them, cars, trucks, bikes, and so on. And then you have the internal dynamic. Each one of these agents is extremely complex. It's a car with someone on board. Well, maybe not anymore in some time, but for the moment, most of cars have someone on board. So the infrastructure, people invented any kind of things, right? This is a double roundabout on UK. I'm sure people have to stop and think before just entering this area. This is a traffic light in New York. No other comment. What about agents dynamics? This is, what is the agent dynamics? Well, we have here mechanical and electrical engineering, and we know how much automotive control has been a big research field to improve our engines or modify them, not to talk about the aerodynamic involved in optimizing the shape of cars. And what about what is inside the car? There is a human. So at the minimum, and we know there is a lot of behavioral traffic, understanding the cognitive process behind driving is surely not an easy task. And, if we want to talk about behavior, there is also some behavior, right, that is not necessarily linked to the cognitive one. Here, I think I noticed this in US a few times, but this definitely was more common in Italy. That's one. And obviously, one of the new things, and this is really the case to talk, and the previous panel mentioned many times, it's just amazing how many people drive looking at their phones. And that is another, it's a very serious issue for safety. Okay, so my final message is don't be scared by mathematics, because don't worry, what you are trying to model and understand every day is way more complicated than all the objects we were talking about. Indeed, those are nice, simpler representation of what is reality and is true very high complexity. So with this last message, let me just use my last slide to thank my collaborators. Obviously, to do this work would be impossible without a set of amazing collaborators. And, this slide goes to thank them. This is just a set of all those that became PI, but obviously I have to thank also all the students that were involved, and that doesn't fit in this big picture. Oh, yes, there is also Sunny. Here we go. And, most of them are smiling. So apparently they have a pretty good time of working on this subject. So I hope you also had some good time attending the seminar. Thank you very much. Yes, that's exactly obviously one may conceive here two approaches. One in which you assume there is a kind of 2D continuum, and the mean field approach would work even if you try to mimic a 2D dynamics. But I think that is more natural what you are proposing, that is using the multi-lanes, because when we are driving, we are not really driving usually in a 2D space, but rather in a 1.5, in the sense that most of the times we stay in our lane. And then when lane changing is usually a maneuver that is more a discrete level, at least to my perception of traffic. So I think that would be the natural way to go. I would rather have multiple equations for every lanes and terms that are pairing them rather than having a 2D unique, even if that would be a possibility.
So what's the current status of theory on conservation laws on the graph?
Mm-hmm.
You talked about this when you have a
right.
bifurcation. I mean, has it been worked out so there's some kind of like unique entropy solution existing?
Yes.
I mean, so for example, if a shock is going down in the highway,
Mm-hmm.
the shock go left or right, or it's a split.
Yeah.
This has been worked out.
Yeah, this has been worked out. So no, what happens is what I presented here, that solver based on two conditions, is something that is kind of natural for traffic. But there were a plethora of other approaches that were designed also because there was interest in many other different domains, like gas pipelines, water, and so on. So interesting enough, for what concerns existence, almost whatever reasonable condition you put there, reasonable means physically sound and mathematically sound, can give you rise to existence of solutions. Uniqueness is much more delicate, but uniqueness essentially you try to explore uniqueness in the set of solutions that respect this dynamics at the junction you prescribe. In some sense, in conservation laws, we can prescribe a Riemann solver, and we prescribe Riemann solvers at junctions, and then we can achieve uniqueness. Now, the last comment is that continuous dependence is very interesting, because continuous dependence strictly depends, sorry, the use of words, on the specific features of your Riemann solvers at junctions. For instance, if you take just that solver, we can have a counterexample to Lipschitz continuous dependence. But if the solver is more like inverting those two criteria, like is natural, for instance, for data networks, where packets can be redirected easily, then you obtain Lipschitz continuous dependence. So essentially, there is a well-rounded theory, but the complete well-posedness depends strongly on the physics of the dynamics at the junction.
For a single one, is it a contraction in L1?
For what? For if...
so again, you do it on a network.
No. It's essentially never a contraction in L1, even when you have a simple junction, because you have a more complicated waves. One of the main reasons is that these waves there are big waves that may be generated from the junction because of the network structure and then bounce back. And this prevents to have a contraction in L1.
Is this BV?
Yes. You can control the BV. You will have that in general over the network will increase in time, but will never explode. Yeah.
So in smart cities where there's hundreds of sensors throughout the city that use to change traffic lights, how different is the math that they use from traffic lights?
Well, I guess that it depends on who you're talking, right? I'm sure that in smart cities, so many people are working, and there are going to be a lot of different approaches. Yeah, I would say that here we are trying to optimize something. I mean, the main difference I would say is that if you have a traffic light, these are fixed location actuators, while these actuators are traveling along the network. And that, I would say, is physically the biggest difference. And that probably would reflect in which type of math you would use. So being the control point fixed, you may use many other different approaches. I believe that since these have this dynamic component to the actuators, I see this mean-field approach as pretty natural and could give a robust math framework.
So the stop-and-go waves or the right-hander bouncing with kind of the fixed light, was that an entropy solution?
Oh, that's interesting. Those are data, right? So they are surely not entropy solution for the LWR. Okay. The way in which people try to understand those waves, there were, multiple work and discussion inside both the more traffic engineering and math community, but there is at least a couple of interpretations. If you move from one equation to two equations, like our Raskol or more general equation, then you may have that. You could have waves up and down in that respect, in that way, okay? So there could be still entropic waves, but for two equations, so more complicated one. There is another interpretation was pretty successful. They call them gemitons, and essentially is again taking a second-order system and adding a source term, that is like a relaxation term, that has some resonance with respect to the speed term. If you do that, you create a kind of metastability, and so you may generate those waves even from close to equilibrium. So they have been investigated, and we do have at this point both a microscopic and macroscopic model reproducing those waves. Yes?
I didn't completely understand the math bit, but
Me neither, so don't worry.
So, two questions. First, try to understand what you did, and second, if I have the questions I had. The first one, am I understanding it right, that you're extending what you did to the ring to make a scripture row very small to them?
That's correct.
Right. So then, when the autonomous vehicles are trying to, when their control is active to control the traffic behind them, isn't that also when the vehicle following the AV is also trying to maneuver to take the chance? So like using that in front of them, so that they are more likely to lane change than it would render the model inefficient?
Yeah, you got exactly the point and the main difficulty. So if we would have, for instance, two lanes in which there is an AV just on one lane and the AV tries to slow down a bit, most likely there would be some car dropping in front. And I don't have yet a solution. What I can tell you is that the project just started. So we have some hope to address and solve that problem, but you got one of the main points. Obviously, our idea will be that we will distribute AVs not on a single lane, and most likely we will still act automatically just as a longitudinal control. And automatic lane changing is still something I would say pretty far away in the future. We are considering also having a mixed situation in which the longitudinal control that is commercially available, because the current ACC are essentially already on cars, automatic, and the lane change human executed. So that could be a potential solution we would envision. But definitely you got one of the main points.
So the tradition of the seminar is that we give you a bottle so that in addition to texting and yelling at people in Italian in the car, you can also drink Chianti.
Oh, perfect. Thank you very much.
Okay. So thank you so much again for the seminar. I want to again thank Sean, Susan for the organization of the day. For our visitors, welcome to Berkeley. Congratulations again. You've been admitted to Berkeley legally. That's great. It's important because that differentiates ourselves from other competitors in California. So I think next is for you, you have office hours with some faculty at 5 o'clock. And then at 6, I believe the students will take you for some after-hours activities in the city of Berkeley. And then final word for those who are coming from places where the weather is nice. This is the absolute worst weather during the year. So this is the tornado at Berkeley. So that, this is really a lower bound in the true mathematical sense of the term. But the rest of the year is absolutely spectacular. So thank you again so much, and good evening.